Then there's a
Yeah.
Really, some people may not be as smart as us, and they may not have done all the other questions.
All right. Power series. So we last time we talked about Taylor polynomials and Maclaurin polynomials, and we talked about how we went about approximating a function with a polynomial. Well, the higher the degree of the polynomial, if we include more terms, the better the approximation is going to be. And what we want to do now is represent a function by an infinite series. And we can represent a lot of functions exactly by an infinite series that we call a power series. So we're going to define a power series. So a power series is the sum, and I'm going to start at 0 to infinity, of a sub n x to the n. And so a few terms, we'd get a0 plus a1x plus a2x squared plus dot 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 plus a sub n x to the n. So this would be centered about 0. And if we center at some other number, we get a sub n x minus c to the n. And here we x is a variable. So that's what makes these a function. So we think of power series as a function of x. And we say the domain of the series or I guess domain is a singular, is the values of x for which the series converges. So we're interested in two things. We're interested in modeling a function with a power series, and we're interested in, well, what if we model this function with this power series, what is the domain of that function? When does that series converge? So we have three possibilities for a power series. All right, everybody good with our definition? So for our convergence, so I'm going to say our power series is centered at C. The first one is our series will converge only at C. That's not going to be a particularly useful power series if it converges at one point. 2, it can converge absolutely for x, absolute value of x minus c less than r, and diverge for x minus c greater than r. where r is some real number greater than 0. So we have some range of x values for which our series converges. And our third possibility is that our series will converge for all x. And it's nice when we have a power series that converges for all x. And exactly one of these is going to be true. Not all of them, not two. Well, if we construct it so that it's centered at C, it will converge at C. All right, so we call R, this value R, is the radius of convergence. And we call it the radius of convergence because if you think of a series in more than one dimension, you get a little circle around your domain values where your series converges, not just an interval on the real number line. Yeah.
What if x minus c is equal to r in case 2? And you broke
but it's less than or equal to.
Well, I'll talk about that separately. That's a separate thing. So if we have convergence only at C, then we say that R equals 0. And if we have if we converge for all x, we say the radius is infinite. So we have an infinite radius of convergence. And the set of x values for which our series converges is called the interval of convergence. So we have a radius of convergence, and we also have a set of x values that we call our interval of convergence. And then to answer Michael's question, we need to determine the convergence of our series at the endpoints of the interval when x minus c equals r separately. The endpoints of the interval converge independently of the values in the interval. So the endpoints converge independently of the convergence or divergence, or the convergence, I guess I should say, inside the interval. So we could have a divergence at one endpoint, convergence at the other endpoint. We could have both converging, both diverging, or one or the other on either side. So we have to test those separately. We test them separately by plugging in the x value for the endpoint and then determining the convergence or divergence of the series that results. So then we're doing our tests, our other tests for convergence that we already know. And our big test, two big tests for convergence of series, power series, are going to be our ratio test and our root test. All right, so let's look at an example of determining the convergence or divergence of a power series. And then I'll talk about some things that we can do with power series and how we might find power series representations for functions. Or I guess one way that we might find. We have n equals 0 to infinity, minus 1 to the n, x plus 1 to the n over 2 to the n. And we want to find the interval of convergence. Yeah, for this one we can use the ratio or the root test. Either one would work. The root test works pretty nicely. So let's look at the limit as n approaches infinity of the nth root of, we're just taking the absolute value of this, x plus 1 to the n over 2 to the n, which is just the limit as n approaches infinity of x plus 1 over 2. And this should be the absolute value. I guess I should have the absolute value in here. And what do we need here? We need this to be less than 1. Well, this doesn't depend on n. This quantity doesn't depend on n. So we're looking at what values of x for which we have x plus 1 over 2 less than 1. Well, that tells us that the absolute value of x plus 1 is less than 2. And we can do this a couple of different ways, yeah?
Shouldn't we have set it up, so got rid of the absolute value bars first and set it up so it's -1 greater than x plus 1 over 2 greater than 1? So you end up with that interval first, or should we?
You can do it either way. Because if you do it that way or the way that I do it, then we get -2 less than x plus 1 less than 2.
But before you start adding or something.
Yeah. And the other way that you can do this, the way I usually think of absolute values, you can set up the interval like this. You can also say x plus 1 is less than 2, or negative x plus 1 is less than 2. You get to the same place. So so our radius of convergence is 2. Where is this power series centered? -1. So we're centered at -1. Because it's x minus -1. So x minus -1 to the n. So our radius is 2. We're centered at -1. So what's our interval? -3 less than x less than 1. Right? So this is our interval. So our possible interval of convergence is between -3, whoops, and 1. So we need to test the endpoints. So it's going to, our power series is going to converge on this interval, -3 less than x less than 1. But it might converge at the endpoints.
No, it's not.
So we need to test.
That's what I like. It's actually not good.
We test the endpoints. So at x equals, when x equals -3, we have the sum, n equals 0 to infinity, of -1 to the n, -2 to the n, over 2 to the n. Wait, look, did I do this right?
Why couldn't you just stack it up?
Can you just get to the?
Pretty much just.
Can you just get to like one of your last steps where you said x plus absolute value of x plus 1 over 2 is less than 1?
Diverges. It's divergent.
And plug it in there instead of plugging
Yeah.
it in here.
Already done.
Plug it in here.
Yeah.
Why is that helpful?
Huh? You could, I guess.
That's way easier to work with. Should we look at it and say that's not less than 1?
Okay, you could do this. You could do that. I like testing them separately.
Because when you plug that in, you just get -1.
We get so let me finish with this one. So -2 to the n, -1 to the n. The -1 to the n's, they cancel each other out, and we just get the sum n equals 0 to infinity of 1, which diverges. At x equals 1, we have the sum n equals 0 to infinity of -1 to the n over 2 to the n over 2 to the n, which is a sum n equals 1 to infinity of -1 to the n. Does that equal 0? -1, if we sum -1 to the n, +1, -1, +1, -1, positive, is that 0? No. It might be if you're a physicist. What's that? Oh yeah. I was deleting the first term. We could do that. All right, so both the endpoints diverge. So our interval is -3, 1. So that power series would converge between -3 and 1. All right, so a couple of things that we can do with power series. Power series are differentiable. On their interval of convergence. So we can take the derivative of a power series and get another power series that converges on the same interval. And I'm going to say the power series are integrable also. Integrable on the interval of convergence. The radius of convergence of the new series obtained is the same. The interval of convergence might be different. So the endpoints, we need to retest the endpoints. So the interval might be different. So if you take the derivative of a power series or you integrate a power series to get a new power series, you need to test the endpoints. So what I want to do next is, last time we came up with a Taylor polynomial, came up with the fourth Taylor polynomial for f of x equals 1 over x. So what I want to do here, and we expanded about x equals 2. So we said that p sub 4 of x was 1/2 minus 1/4 times x minus 2 plus 1/8 times x minus 2 squared minus 1/16 x minus 2 to the third. Let's find a general expression for the nth term.
Are we allowed to start at 1? We have to start at 0.
We have to start.
Yeah, for a power series, we want to start at 0 because we want that constant first term. So what we're looking for is a pattern. So let me do one thing to help us out here. I'm going to factor out a 1/2.
Ow. Ow. Feel bad. Actually, shouldn't that be
Oh, then that's
negative
all.
1/2?
Yes. All right, so we want to look at this pattern and see if we can find an expression for the nth term. So I'm going to say p sub n of x equals, I'm going to have this 1/2 here. Well, we know that we alternate signs, right? So I'm going to put in a -1 to the n. Let me put a parentheses here. So we need a -1 to the n to get those alternating signs. These coefficients, 1/2 to the n, and then the powers here, x minus 2 to the n. And I'm going to combine these two together and write this as, well, actually I'm going to kind of combine all of this together, and I'm going to write this as minus x minus 2 over 2 to the n power, and then I have that 1/2 out front. So we could say that f of x, 1 over x centered at x minus 2, is 1/2 the sum n equals 0 to infinity of minus x minus 2 over 2 to the n. When is this thing going to converge?
What root test would you use?
What is it, Connor?
Geometric.
This is geometric. This is r, the sum n equals 0 to infinity of r to the n. So we don't have to do any of that. This is geometric.
Isn't root test like part of the hand of geometry? Because if it's a good thing for root test, it means there's a power of n on it.
But you could, for a root test, you could test something like n to the n over n factorial. You could test that.
It's one that's like, wow, that should be a root test problem. It's because they all have, a lot of them have an n,
Right.
power of n, so they would mostly be
Not necessarily.
Or geometric.
So, yeah, so geometric-ish. Yeah. Yeah, and the root test, the proof of the root test, you end up comparing the series to a geometric series.
It's
So
related to geometric series, but it's more useful.
right. Well, ratio test is related to geometric series also. All right. So when does this converge? All right, folks. Let's stay focused. When does this geometric series converge? When
Or x minus 2 divided by 2.
absolute value of x minus 2 over 2 less than 1. So we have x minus 2 absolute value less than 2. So we have negative 2 less than x minus 2 less than 2. So we go from negative 4 less than x less than 0. The other way around. 0 less than x less than 4. There we go. But wait, geometric series, what do we know about geometric series? You don't need to test the endpoints because we know geometric series diverge at the endpoints. So our interval of convergence is 0 to 4. So that would be a power series. This would be a power series for 1 over x centered at x equals 2 between 0 and 4.
So, Mr. Beamer, the one that we did before, the negative 1 times the x plus 1 to the n divided by 2 to the n, that's another, we could put all that under to the n and just say that.
Right.
that was
Yeah, you could. Yeah, pull out the n.
That's why I was bothered by that.
Ah, okay.
So, and then which ones of the special series are we supposed to know? Sin x, e x, cosine x?
We'll talk about those next time.
Oh, okay. You already
I
said
think.
that.
Yeah, we talk about those next time. So what we're going to do next time is one, we're going to exploit this geometric series thing, and we're going to use integration and differentiation to find new power series. So we can. This is a power series for 1 over the x, 1 over x. We could integrate that to get a power series for natural log x, for example.
That's not okay.
All right, there you go.